Hi everybody, welcome back. We are going to start into our next unit in our series on AP Physics C, Electricity and Magnetism. I usually reserve a separate unit for a discussion just on Gauss's law, not only because for people actually taking AP Physics C, E, and M, this is a very common problem on the free response part of the AP exam. About 80% of free response tests have a Gauss's law problem, but also because the skills that are developed in using Gauss's law to solve problems and to solve for electric fields can be further utilized when we're dealing with not just charge distributions later on, current distributions. So without further ado, let's get to some motivation for Gauss's law. So what we're going to discuss in this video is going to be the calculation of electric flux, and then a really cool result that we will end up using for the rest of the unit. So we've been hinting at this occasionally, even when discussing just relatively asymmetric charge distributions, and how if the charge distribution was symmetric, we would be able to use Gauss's law to make our lives a lot easier. It's an extremely powerful tool that makes it so that we do not actually have to utilize multivariable calculus in order to determine what's going on with these charge distributions. It's also one of Maxwell's equations. In fact, what you're going to find is that this entire course is going to be building toward Maxwell's equations, and then we'll have a discussion on those once we get all of them near the end of the course. So let's first consider some symmetries. If you have an infinitely long cylinder, there are four symmetries that are worth considering with the cylinder. First, translation parallel to the axis. That is, if it's an infinitely long cylinder, no matter how far you go up or down the axis of the cylinder should look the same if you're going to be able to do anything with this infinitely long cylinder using symmetry properties, i.e. Gauss's law, later. Rotation about the axis, in other words, the appearance of the cylinder should not depend on the angular coordinate, theta or phi, depending on what you want to call it. Reflection in a plane containing the axis, in other words, if you imagine a plane perpendicularly bisecting your cylinder, then looking at it upside down versus right side up should appear the same. And finally, reflection perpendicular to the axis. In other words, if you have an axis that bisects, or at least is perpendicular to the axis of your cylinder and bisects with it, then rotating about that new axis by 180 degrees, or pi radians, will not change the appearance of your cylinder. So those are the four symmetries that are worth considering with this cylinder. The reason we want to talk about symmetries is because, as we're going to discuss soon, Gauss's law is only going to be useful for calculating what's going on when certain symmetries are in place. So if these symmetries aren't obeyed, you won't be able to solve exactly for the electric field at some arbitrary point far away from the cylinder. You might be able to solve for it for certain specific points, but not E is a function of x and y and z. So at best in that case, you would need to use a simulation to estimate the electric field, to approximate what it is. So overall, there are basically three shapes that will allow us to use the tools that we're going to develop. An infinitely long cylinder, like what we just discussed, a sphere, or a point for that matter, which is a trivially small sphere, and an infinite plane, or a bunch of infinite planes stacked on top of each other. Now, just because you have these sorts of shapes doesn't necessarily mean that you always will be able to use the tools that we're going to develop. In other words, you need the symmetries that are necessary in order to be able to actually use Gauss's law. For example, you could have a sphere, but if your charge distribution is not constant as a function of theta and phi, then you will not be able to use Gauss's law. Okay, so this is especially important for thinking about the infinite limits with cylinders and planes. So in these scenarios, the electric field, since it remains unchanged under those symmetries, it will be able to be calculated using this Gauss's law. But in order to talk about that, we need to talk about electric flux. we've talked about electric field lines before. You could think of flux as a measure of the number of electric field lines coming out of a surface. And you could just leave it at that. But we actually have a mathematical definition of electric flux. So, depending on the angle at which the electric field comes out of the surface, that's going to be a different amount of flux. In other words, if you tilt your surface, that's going to mean that less electric field lines are going to come out of it than otherwise would. So the angle is going to matter as well. And electric flux is going to be what's going to allow us to come up with this idea of Gauss's law. So let's consider these surfaces. So in the surface on the left, you see that there are a number of electric field lines coming out, and the surface on the right, there are a bunch more electric field lines coming out. But if we were to rearrange the shape of our surface, we would still have the same amount of flux in each of these situations, as long as we don't end up losing any of the charge that is causing these electric field lines to exist in the first place. So on the right side, because we have far more electric field lines, you recognize that the right surface is enclosing far more charge. But again, if you were to reshape that surface, as long as it contains the same amount of charge, the same number of field lines are going to be coming out of it. That's an extremely important point that we're going to come back to later. Now I should note that these are very definitely not conducting surfaces. How can you tell? I'll give you a few seconds to pause the video to think about how can you tell that these are definitely not conducting surfaces. So, if you have thought about why these are not conducting surfaces and unpaused your video, the reason is because there are certain situations where the electric field lines are clearly not perpendicular to the surface, which means that there must be some concentration of electric charge that ends up creating an off-normal electric field. Well, an off-normal electric field will end up causing charges to move around until that has been canceled out. If it's a conductor, when charges are able to move around, but if it's an insulator, the charges aren't necessarily allowed to move around, and you can end up having these off-normal electric field lines, like what we have right here, coming off over here, and what we have over in this area coming off at this angle and this angle. So these are definitely not conducting surfaces, because the electric field lines in a conductor are always normal to the conductor's surface. So again, you can think of flux as the amount of electric field passing through a surface. So first, we realize that there's an outward flux through a closed surface around a net positive charge. There's going to be an inward flux, therefore, through a closed surface that is around a net negative charge, because electric field lines go into negative charges. And if there is no charge inside of your surface, then there will be no net flux. That doesn't mean that electric field lines can't go through your surface. It just means that any electric field lines that do pass through your surface are also going to pass back out the other side. That's an extremely important realization that we're going to make use of later in this discussion. So, electric field passing through a surface is given, mathematically speaking, by this potentially intimidating expression. The double integral, of the electric field vector dotted with the infinitesimal area of the surface. Now, in some situations, we might actually have to calculate this integral using calculus, and that's just something that would potentially have to be done. Now, generally speaking, in this class, whenever you do need to use calculus on something like this, there will be some degree of symmetry that will allow you to replace this with a single integral. For example, maybe the electric field is only a function of y and not x or z or anything like that. So in those situations, it'll just be one integral that you'll be able to deal with. But in general, including all possibilities in higher level physics, this is the equation for the electric flux through a surface. Now, it's evaluated over the whole surface. If the electric field is constant in magnitude and direction across the surface, then the integral is very easy. In fact, if the electric field is constant with respect to the direction from the surface, in other words, with respect to the normal vector coming out of the surface, then this is also very easy and you won't have to do any calculus at all. So we're going to examine those situations soon. So note that we're not making any statements yet about whether this is a closed surface or an open surface. In other words, this could just be the formula for the electric flux through a square, or a rectangle, or a pentagon, or a dodecagon, or something like that. Or it could be closed, like a dodecahedron, or a cube, or a sphere. Now, the integral here, remember, is just a fancy way of doing a sum. In other words, you're adding up all of the individual flux contributions. In other words, you divide your surface into a bunch of little bitty areas, multiply the electric field that is coming through that area, times the area itself, times the cosine of the angle between the electric field vector and the area vector, and you get your individual little bitty electric flux contribution. What do I mean by the angle between the electric field vector and the area vector? The area vector for a surface always points directly out from the surface. It's always normal to the surface. So if the electric field is also normal to the surface, that angle is 0, and cosine of 0 is 1. Let's take a look at some easy flux calculations. So if the electric field is constant over the surface, and the angle is constant with respect to the surface, then the flux is just going to be EA cosine theta. Or again, theta is the angle between the electric field vector and the area vector coming out of the surface. That is, pointing directly outward from the surface. So what we mean by that is, in this picture, let's say we have some rectangular prism in this situation who has a top surface that has an area of capital A. Well, in that case, the area vector for the top surface will be a vector of magnitude A pointing directly up, since it's the top surface, and that magnitude given by the area A, and notice it's multiplied by a unit normal vector. In this case, the unit normal vector points up. So if, let's just pretend that there was a constant electric field pointed in this direction given by the blue electric field vector, and the angle was theta between the electric field vector and the area vector, and if that electric field was constant over the whole surface, then the electric flux through the top surface would be given by EA cosine theta, where the theta is this theta. Be careful, because you will sometimes encounter problems where they give you an angle, but the angle that they give you is not the angle that is with respect to the normal for the surface. So that's just something to keep in mind. And you can also come up with something, you can make similar analogies, for example, like the volume of air per second going through a closed surface would be equal to the velocity of the air vector dotted with the area vector of that surface. So that if it's just going straight through the middle of the surface without any funny angle, then that volume of air per second is just given by velocity times area. However, if it is going through at some angle, then the flux of air, the volume of air per second, would be VA cosine theta, where theta is the angle between the direction of the air particles and the area vector of the surface. In other words, the vector going into the surface, or out of the surface, so to speak. Now, keep in mind that there are two types of fluxes that we're going to deal with in this course. Well, many types of fluxes in general, but two that we're going to deal with in the course. A lot of times people will use the subscript E to denote the electric flux. Later on in the course, we're going to have a subscript B to denote the magnetic flux. Why B? Because B stands for magnetic. No, because M is taken by lots of other things, so they decided to use B. Let's take a trivial example in this poorly drawn situation where we have a uniform electric field of 93 million newtons per coulomb at an angle of 72 degrees with respect to the surface. Calculate the flux going through this rectangle surface, or at least we'll consider the magnitude of it, since it's hard to tell how the surface is oriented. So we write down our givens. So we have the length and width of the rectangle. Make sure to convert to SI units. The electric field, and the angle. Oh, wait a second, I thought it was a 72-degree angle. Ah, but 72 degrees with respect to the surface. That's not 72 degrees with respect to the normal of the surface. it's 18 degrees with respect to the normal to the surface. So it's the 18-degree angle that we need. So just keep that in mind. They will often try to trick you, especially on multiple choice questions. So here are our givens. Here's our equation. And notice how we rewrite our equation so that the area in the equation, well, area wasn't given to us in the givens, but the length and width were, but area is equal to length times width. So flux is equal to ELW cosine theta. And now we plug in our numbers and we shove them into a calculator and get an electric flux of 12 million voltmeters. A voltmeter. So there aren't any cute names for flux units, but maybe you can come up with one if you become a really famous physicist. Now, it turns out that Newton meter squared per Coulomb is the same thing as a voltmeter. That's something we will discuss in more detail when we start talking about electric potential in the next unit. So, keep in mind that when evaluating fluxes, if it's not a simple case like this, then you'll need to divide your surface into multiple regions. You might even need to divide it into infinitely many regions. That's called an integral, and add them all up. Now, remember again, the surface is always normal. If you need to divide them into such regions, then a lot of times you will find it easiest to do so where you make them into regions where the flux is either zero, i.e. the surface is tangent to the electric field. That's going to give you a 90-degree angle in that cosine. Or where the surface is normal to the field, a 0-degree angle in the cosine where you just have an EA. Now, it's the second of these cases to which we're going to apply Gauss's law, which is what this unit is all about. And the thing is, in Gauss's law, you create your own surfaces. Now, what if the surface is closed? If the surface is closed, then the equation for flux, it's the same, except you have this little funny loop on your integral. That's just telling you that you're integrating over the entire closed surface. And this looks really intimidating. When I first encountered this when I was in college, it looked really intimidating to me. It turns out it shouldn't be intimidating, because the integral is, generally speaking, either easy or trivial. So we're going to look at a situation with this in just a minute. So again, because the field on your particular surface is generally going to be constant, a lot of times that electric field is going to pop out of the integral. Situations that you're going to encounter in this class, or if you're taking a 200 level college electricity and magnetism course that is part of the typical curriculum for first-year engineering and physics majors, then the only types of integrals you're typically going to have to evaluate will be one-dimensional integrals anyway. Now, if it's a weird sort of surface, then you might have to use some sort of advanced mathematical technique that will simply give you an approximation in the end. But in my particular class, every surface integral can either be easily evaluated on paper, or a lot of times in your head using symmetry. So if that's not the case, then you're not going to be able to use Gauss's law to solve the problem anyway, and that's what this whole unit is about. So again, two main simplifying cases. If the electric field is tangent to the surface, then the flux is zero. If it's constant and perpendicular to the surface, then the electric flux is E times A. And we're now going to turn our attention to that second situation. Here's our example. Calculate the electric flux through a sphere of radius capital R that surrounds and is concentric with a point charge of magnitude capital Q. Well, here's the thing. At any particular distance, capital R, away from that point charge, the electric field there is constant. We already know that. This is from Coulomb's law back in chapter 26. So the direction is also constant, because since our sphere is concentric with our point charge, at least we're assuming it is, then the electric field is always going to be pointing radially outward from our surface. In other words, it's going to be pointed in the same direction as any unit normal vector at any particular part of that surface. In other words, if you pick a point on that surface, the angle between the electric field and the normal to the surface is always going to be 0 degrees. So the integral becomes trivial. In other words, your electric field is constant. We're going over the whole surface of the sphere, so the area is known to be 4 pi r squared. You'd better have that memorized by now if you're taking this course. So, since the electric field is a constant kq over big R squared, the area is a 4 pi big R squared. Look at that. The r squareds cancel. In other words, the electric flux is independent of the size of our sphere. So the r squareds cancel. You're left with a 4 pi kq. And do you remember what 4 pi k is? Of course you remember what 4 pi k is. Yeah, it's 1 over epsilon naught. So that's useful. We can use that little simplification and realize that the electric flux from a point charge, independent of the radius of our sphere, but the electric flux through the surface of the sphere that surrounds a point charge is the charge itself divided by epsilon naught, where epsilon naught is the permittivity of free space, about 8.854 times 10 to the minus 12 coulombs squared per Newton meters squared. Now, this is an amazing result. The fact that the electric flux is independent of the radius of your sphere leads to a remarkable conclusion. The electric flux through any sphere is equal to the enclosed charge divided by epsilon naught. Any sphere. In fact, because of the fact that if a surface not containing a charge will just have any electric field line going in, also coming out, you can imagine pasting a few other surfaces on top of your sphere and around your sphere so that it becomes shaped like a kidney or anything you want it to be shaped like, and realize that the electric flux through any closed surface of any shape surrounding any charge is equal to the enclosed charge over epsilon naught. In other words, this is a general result, and it's one that you should definitely memorize for the rest of your lives. So here it is, again, the electric flux through any closed surface, which is defined by this integral, turns out to be equal to the enclosed charge divided by this epsilon naught. So again, you can kind of think like, what if there are a bunch of charges sprinkled around? Well, what you do is you surround each of those charges with a sphere, make the sphere small enough such that that sphere is only enclosing that particular charge. And then it's like, okay, well, you have a flux from one sphere, you have a flux from another sphere, you have a flux from another sphere. And then you can fill the area in between your spheres with shapes of whatever shape you want, because you know that since those shapes don't enclose any charge, any field lines going into those shapes will also come right back out of those shapes. So they're going to have zero flux. So that means that any sprinkling of charge, surround it with any surface that you want, the flux through that surface is equal to the enclosed charge over epsilon naught. This is an extremely important result. This is called Gauss's law. Now, interestingly, this Gauss's law is also valid for moving charges. It might be more difficult to use, but it is still valid. On the other hand, Coulomb's law fails spectacularly for charges that are moving at high speeds, particularly relativistic speeds close to the speed of light. But Gauss's law will still remain in operation. So this applies not just for the rest of this unit, but really for any situation you can conceive of. So we will have some more practice actually using Gauss's law, starting with the next discussion. I'll see you all then. Thank you for watching.